Hello everyone. Welcome again to the solid state physics course. So in the last lecture, we read about how to calculate the mean free path from Drude's theory, and we talked about the limitations of Drude's model. So it basically was successful in explaining many interesting phenomena. Still now, many approximations are being done with this theory, but it falls at certain points. It is not able to explain everything. So now, in today's lecture, we will start with AC electrical conductivity of a material. So let me just write. So AC, yeah, AC electrical conductivity of a material. All right. So now you consider an electromagnetic field. First, let us consider an electric field. So, an electric field uh, can be written as, let me just change color. So, vector E, this is a E, is equals the real part of, which depends on the frequency, e raised to minus I omega. So if this is the form of the electric field, we expect that the momentum E vector, we seek solution for E vector T of the form E vector T equals the real part of E vector omega into e raised to minus I omega. So this is for, this is solution for steady state. All right. So now recall Drude's equation, which is E vector T equals to minus E vector by tau minus plus a force. This is a uniform force, especially uniform force. Now put the form, the form that we have written here. So putting this form in the above equation, this is through this equation. So ddt of E vector omega raised to minus I omega t is equals to minus E vector omega raised to minus I omega t by tau minus E of E vector omega e raised to minus I omega t. So the force here is given by the electric field. So now you can easily calculate E raised to E of omega into minus I omega raised to minus I omega t is equals to minus e omega e raised to minus I omega t over tau minus e electric field E is to minus I omega t. So cancelling e raised to minus I omega t on both sides minus I omega e of omega is equals to minus e of omega I tau minus e of. All right. Now this implies omega I omega minus 1 over tau equals e. The electric field vector. Understood? So now implying E of omega is equals to E of electric field vector divided by I omega minus 1 tau, again equal to E tau E vector omega by I omega tau minus 1. Now we know about current density. Current density. J vector, sorry, J vector minus n e b vector is equals to minus n e b vector over m. So you can understand where we are going into. So we will be using this form of current density in your momentum. So all right. So now again, the current density J vector T is earlier so J vector omega equals to minus n e e vector omega by m. This is simple to understand. Now what we want to do is we have to put this form in P of omega. So J vector omega is minus n e by m into, we have gotten earlier the E of omega. So this is equals to E tau E vector omega by I omega tau minus 1. Therefore, so we have vector signs minus, so this is n e squared tau over m into 1 minus I omega tau. Interestingly, this n e squared tau over m, this we got earlier. This we got earlier. This is an additional term here for the AC applied electric field. For DC conductivity, this is your sigma, or you can say sigma naught. So your sigma naught is DC electrical conductivity as obtained earlier from Brooks equation. Fine. So therefore J vector omega equal to sigma naught into, sorry, there should be E vector into 1 by 1 minus I omega tau into E vector. Now we have a form, an AC form of the current density, and now we also have a form, an AC form of the conductivity. So this is similar to the DC conductivity, except for the fact that a term 1 by 1 minus I omega tau is added. It's multiplied in fact rather. There are some clarifications that I need to make in that. What we have said earlier is that this force applied is a spatially uniform force. But you know that an electric field is spatially varied. So an electric field can be written as e raised to I x minus omega t. So this is the spatial part. Spatial part. So what happens now? So as the electric field is varying, you have to take into account what is the length scale over which it is varying. All right. So for an electric field, to affect electron at position r, has to do so since the electron has last undergone a collision. If you recall the second postulate of the Joule's theory, we said that in between two successive collisions, the electron can be affected by electric or magnetic field. The same sentence I'm reiterating here is that in between this two collision, it can be affected by an electric field, and the electric field can affect an electron at a position r. So since his last collision, it can be affected by that electric field at position r. So, and if you connect from last lecture that uh, in realistic case, because electron is a quantum particle, we clarified that the mean free path is not of the order of lattice spacing or the distance between the ionic sites. It is at least 100 to 1000 times larger. So maybe at most the electron can traverse mean free path twice or thrice lattice spacing. Okay. So at most it can traverse a distance which is twice or thrice than the lattice spacing. So if the electric field is not varying over that length scale, which is twice or thrice the lattice spacing, then you can safely approximate that the electric field is not spatially varying. So over that length scale, it will not affect, it will not be different at position r than what it was at position r plus del r, right? So now you can safely make that assumption electric field is not varying over the length scale traversed by the electron. All right. So an electron, so we draw the ionic sites here. After undergoing this can be at most thrice or twice the lattice spacing. So in between this length scale, you can understand that you can safely approximate that the electric field is not varying. So on last day, the length scale we talked about is 100 to 1000 angstrom, and this this is the length scale. All right. So the electric field for visible light, it satisfies this criteria. So in respect to this, in respect to this, the wavelength of the electromagnetic field has to be taken into consideration. Fair enough. The so lambda has to be larger than the length scale traversed by the electron. Fine. So this criteria is satisfied only by visible light. 10 raised to 3 to 10 raised to 4 angstrom. So the electric field is not spatially varying over that length scale. So you can safely approximate that the electric field remains constant over the length scale traversed by the electron. So Ft, which was considered to be a spatially varying force, spatially non-variant force, it is satisfied by the electric field now that we have this assumption, now that we have this consideration. All right. The second point is that, so this is the first point. This is the first point. The second point is that we did not consider the magnetic field. Total Lorentz force is given by FL minus E vector minus E vector by C cross H. So this is the electric field part. This is your magnetic field. All right. So now carefully we have to calculate the order of magnitude for the second, whether we can ignore or not. We'll see that we can safely ignore it. So J vector is minus n e vector, which implies E vector is minus J vector by n e. Now if you take the magnitude only, from last day, if for J equals 1 ampere per millimeter squared, which is 1 ampere per 10 raised to minus 3 meter square, which is 10 raised to 6 ampere per meter square. And from last lecture, we calculated n is of the order of 10 raised to 22 to 10 raised to 23 electrons per cc, which is 10 raised to 22, 10 raised to 23 divided by 10 raised to minus 2 cubed. So this is equals to 10 raised to 28 to 10 raised to 29 per meter cubed. So n 10 raised to 28 to 10 raised to 29 electrons per meter cubed. So converting all in SI units. All right. And E is 1.6 into 10 raised to minus 90 all in SI unit. So we can estimate G is 10 raised to 6 amperes per meter squared. N is 10 raised to 28 to 10 raised to 29 per meter cubed into 1.6 into 10 raised to minus 90 minus 90. So 10 raised to 6, 10 raised to, let's say 29 into 10 raised to minus 90. 10 raised to 6 by 10 raised to 10 equals 10 raised to minus 4 meter per second. So V 10 raised to 4 meter per second. Now electric field part was minus E vector, and the magnetic field part was E vector over C. So an extra term, an extra factor, dimensionless factor, V by C is there. So V by C is 10 raised to 4 meter per second. 3 into 10 raised to 8 per second. So 10 raised to minus 12 by 3. This is the factor by which the magnetic field part, this is the factor. This is the factor by which the magnetic field part differs from the electric field. See, this is very, very small. If electric field and magnetic field are on the same footing, but the other is scaled by a factor of 10 raised to minus 12 to 10 by 3. So this is negligible. So our conclusion is that is that the conclusion is that we can do away with the magnetic field, and continue with the electric field only. All right. So now we can proceed. So what we got earlier was J R vector. Now we can include the spatial part is equals sigma omega times E vector. All right. Now we have included the spatial part too, because now we have sorted out all the approximations and the clarifications that we needed to. Let's write our very popular, very own Maxwell's equation. All right. So Maxwell's equation. Why am I writing this? The immediate application in finding that the dielectric constant will be, uh, we will get this the form of the dielectric constant from this very equation, which is JR is equals to sigma times E. So in CGS. Fine. So presence of only current density. Presence of only current density J. So mess up sometimes. The consider that rho charge density, volume charge density vanishes. So in Gauss's law, divergence of E is 0. Divergence of the magnetic field is anyway 0. Curl of electric field is equals to minus 1 over C times del H. And the final form is curl of H is equals to 4 pi over C times J vector plus 1 by C del E del E. We're done. Now this is 1, this is 2, this is 3, and this is here. And this is 4. So operating a curve on 3. So curl of E equals 1 over C curl of J plus 1 by C. You can interchange the spatial and the temporal part. So this is curl. All right. So now from the basic cross product of gradients, this is given by gradient of divergence of E minus Laplacian of E equals 4 pi over C sigma curl of E. E plus 1 by C curl of E is also given by minus by C into H. Sorry. Sorry. I did something wrong. Yeah. So I, this is absolutely wrong. So by mistake, I used the fourth equation. Pardon. So what I was supposed to write is that curl of phi disposes of curl of E equals minus 1 by C time derivative of curl of H. You can interchange the spatial and the temporal derivatives. Alright, so this is gradient of divergence of E on basic cross product rules minus Laplacian of E minus 1 by C. Curl of H is again given by del T of 4 pi over C j vector plus 1 by C del E del E. This is anyway, this is 0 from Maxwell's equation. This is 0. So now minus Laplacian of E equals minus 4 pi over C square del J del T minus 1 by C square del 2E del T. Now, since J vector omega is equals, sorry, times omega is equals sigma omega times E vector. Fine. Let's put it in here. E 1 by C squared del E del D. Sorry. Yeah. Pardon. Now, rad squared E equals 4 pi sigma over C squared del E del T plus 1 by C squared del 2E del E2. Now, continue this. You know, fine. So, therefore, gradient of E is equals 4 pi sigma by C squared minus I omega E vector plus 1 by c squared minus I omega squared. This implies minus 4 pi I sigma omega over c squared minus omega squared by c squared. If you take c common, omega squared by c squared common, which is 4 pi I sigma by omega plus 1 times. Alright. So it rings a bell in your head. So this is your basic wave equation, plane wave equation. Four pi I sigma over omega times E vector. How this is the wave equation? Let me take. So in a non-magnetic, because we are not considering the magnetic field here, non-magnetic dielectric medium, curl of B minus 7 mu that E then T2 permittivity of the medium is equals epsilon r times epsilon r. So permeability of the medium, which is which is r times mu naught. So here for non-magnetic case, mu r equals 1 and epsilon naught and mu naught are the permittivity and permeability of free space. I'm writing that. So and again c squared is 1 by epsilon naught. All right. So we had rad squared E minus omega squared over c squared 1 plus 4 pi I sigma over omega times E. Now we've already seen that del 2E del T2 is given by minus omega squared E vector, because E vector is E naught vector into E times I kx minus omega t. All right. Now this can be manipulated as minus omega. So we had gradient of that square t vector is equals um, mu epsilon del to E del T. Fine. E del T2, which is given by minus omega squared mu epsilon into this E vector. Now we have to manipulate this part to arrive what we need. To arrive at what we need. omega squared over c squared times mu times epsilon times e vector. Now, c squared is minus 1 by mu naught epsilon. So, this is the permeability and permittivity at free space. So, your mu e is given by mu r mu naught times epsilon naught r epsilon naught. This is your dielectric constant. And mu r equals 1 for non-magnetic media. So what you are getting into is minus omega squared over c squared times 1 by mu r naught epsilon naught times mu naught times epsilon r times epsilon naught r epsilon naught times e vector, which is your minus omega squared over c squared times epsilon r times e vector. This is your dielectric constant. This is, can be written as also, you know. So what we had is grad squared e minus omega squared over c squared times 1 plus 4 pi I sigma over omega times e. So this is comparing. So this is your dielectric constant complex in general is complex. Fine. So your epsilon omega is 1 plus 4 pi I sigma over omega. Alright. So sigma is also n e squared tau over m 1 by 1 minus I omega tau, which is given by 1 plus 4 pi I over omega times n e squared tau over m times 1 minus I omega tau. So this can be manipulated as 4 pi n e squared over m times tau by omega times minus 1, multiplying either denominator and numerator by I plus omega tau, which is 1 plus, sorry, this is minus 4 pi n e squared over m times tau over omega by omega t tau plus 1, which is again given by 1 minus 4 pi n e squared over m tau over omega tau minus I, yeah, squared tau squared plus 1. So the real part of epsilon omega is then given by 1 minus 4 pi n e squared over m times tau by omega times omega tau by omega tau plus tau squared plus 1. Now, if we make the approximation that omega tau is much greater than 1, this can be written as 1 minus 4 pi n e squared over m times tau over omega times 1 over omega tau. So let me just write it fully for convenience. This is equals to 1 minus 4 pi n e squared by m omega squared denoted by omega p squared. So your omega p squared is 4 pi m p squared by. So let us just consider two cases where first case epsilon or the dielectric constant is real and negative. That is omega less than omega p. In that case, the solution rad squared e is equals minus omega squared over c squared into 1 minus omega p squared over omega squared times e. This as a whole becomes negative. Sorry, this becomes positive because this part is negative. 1 minus omega p squared by omega squared becomes negative. So the whole becomes positive. So this is an exponentially decaying solution because this is some constant, some positive constant times the p vector. Thus, exponentially decaying solution. Let me just check. It's recording. Second case is epsilon omega is real and omega is greater than omega p. In that case, the grad squared e vector is equals this term, this minus omega squared by c squared is negative, and this is positive. So this is some negative constant times e vector. So this has an oscillatory solution. Oscillatory solution. What happens then? For an electromagnetic field, when trying to penetrate into a material, for the first case, it won't be able to because it will decay down at some point, which will be given by the skin depth. But in case of the second, for the second case, where the direct constant is real and omega is greater than omega p, there's oscillatory solution and the radiation, the electromagnetic radiation, will propagate inside the material. So we should stop here. So today we learned about the AC electrical conductivity of a material and how it can be applied in finding the dielectric constant of the material, and we found out two cases where there's oscillatory solution and there is exponentially decaying solution where the electromagnetic radiation, depending on that, will penetrate inside the material or not. So let us just stop here. Thank you.